Okay, students. So, right. So let's continue now. Um, I hope you are present over here. Okay, shall we start now?
Yes, sir.
Okay, so if all of you are here, so let's move on. So, coming to our next topic, which is how to design these fast multipliers. So we looked at a basic multiplier, that was the diagram shown on the that's the diagram shown on the left side. This is a basic multiplier. So you have an adder, you have an x multiple, a partial product which is going back to the adder, and then you finally get this result over here, right? So if you want to improve that design, what we did was we had a small CSA tree which has got several multipliers, several multiples here. So you have got a multiplexer or a CSA tree over here, and there are different multiples coming over here, and then you can have uh, more operands. You can have a bigger radix over here, and then you have many multiples, and then you can do the same thing in a faster way. If you go for all multiples and then you want to join them using a full CSA tree, this is the fastest design here. Okay, so this is actually when you have all multiples and you just have to use a full CSA tree, and then you can have your adder. But this design is also hardware wise quite complicated. So we are now going to talk about the CSA tree design for multipliers. Okay, so for multipliers, the two common trees are the Wallace and Dada trees. Uh, so when you come to CSA trees, it's the carry save adder, and carry save adder, as we mentioned, that the objective is to reduce the number of operands that have to be added, right? So this is the second technique where we are talking about how to improve the multiplication process by making the addition faster, right? So this is about not changing the radiuses, but about making the multiplication operation faster, right? So this is one way, that if you have got multiple operands to add, uh, what you can do is use a carry save adder in that place, and then it's going to reduce that into fewer adders, fewer numbers, fewer operands at each step, and then you are finally going to have uh, a full adder at the last step, a triple carry adder at the last step, and then you can complete your multiplication. So two designs here that we are going to see. There are also different other designs, but Wallace and Data. So Wallace, the thing about Wallace is that, so if you're talking about Wallace and Data, they're both going to take the same number of steps to come to that answer, but in Wallace it tries to uh, use as many full adders as possible whenever it's possible, right? So it combines the partial product as soon as possible. So this is um, uh, its characteristics that it's going to combine the partial product as soon as possible. While in data, it's going to maintain the critical path, which is shown over here. That this is the levels that it's going to have. Uh, so it's going to combine as late as possible. So these are the two different trees here, the CSA trees that we can use for multiplication. And this is a table here showing the number of levels to reach 2. So finally we need to reach 2. We need to have two inputs, two operands that have to be added, right? uh, so for example, if you have got say you have got 10 operands to add, okay? So if you're going to have 10 operands to add, this means it's a 10-bit number. So uh, you have got 10 operands to add, and then 10 lies somewhere here between 9 and 13. So we are going to take 13 here. So it's going to take 5 steps to reach 2. Now what Wallace is going to do, it's going to eagerly join all those partial products. So, but still it's going to go from 5 to from 10 to 2 operands in 5 steps here. So 5 to 4 to 3 to 2 and 1. So actually there are 1, 2, 3, 4, 5, 6 steps here, right? So it's going to take 6 steps here to reach this point over here, right? So we are going to take some examples now. Right. So let's try to see how would Wallace tree do this addition, this addition of operands. So there are 7 numbers here that needs to be added, and we have discussed that earlier as well when we were talking about CSA. So in a CSA, what happens is that you have you can have full adders or you can have half adders, and whenever you are using a full adder, then it's going to give two outputs, 2 bits as output. So one of that bit goes to the same level, and the second bit goes to the next level, which is added to with the second level of operands. So so what we can do here is have 12 full adders, and these 12 full adders are then going to have give us one input at this point, another over here, another over here. So we have discussed about the carry save adder in our last to last class, and this is going to use 12 full adders from reducing it from 7 to 5. So you can see here that there are maximum 5 bits at any particular line over here, any particular column you can see over here. And then you need further 6 full adders over here. You could have used half adders as well over here. So this Wallace tree design here is not the only Wallace tree that's going to happen. So you could have used half adders over here. So whenever you find there is a possibility that you can do and it's going to save some of the circuit time, so you can do that as well. So you could have used a half adder as well. So in a case like this, you would have obtained one more bit over here and then one bit over here. Now what would have happened if you have used a half adder in this case? So this is 3 input over here coming from this point, right? So if you have used a full adder, then one input goes over here and one input comes from this previous level. So you have got 2 inputs. And if you have used a half adder over here, so one input is going to come over here. So this reduces to 3 only instead of 4. It reduces to 3 only, and this level reduces to 1 only. This level reduces to 3 only, and you're going to have one input coming from these 3 to this level, one from this, one from that half adder, and one from. So it's going to be still 4. So that's the reason over here that we have not used a half adder, because in all these remaining cases, the number of inputs are not going to change. So it's going to be still 4, right? But you could have used Wallace tree, because in Wallace tree there is no restriction on when to use a half adder, full adder. You try to combine the partial product as soon as possible. So you could have used half adders over here. So this is just one example. You can have a different one. Right. So after six more full adders, you convert it in from five to four, and then from four to three. So you can see here that the maximum number of operands that have to be added are three. And then after applying four full adders and two half adders, you have reduced it to just two operands here. Of that two operands, two bits are without any corresponding bits for the second operand. So this means that these two bits have been finalized and they are part of the final answer. So you just need to add these six bits. So you need a six-bit adder at the last step, and then your multiplier is complete. So multiplication is all about addition of partial products. So if you have got partial products, so the thing is, where are you going to get these partial products from? Right? So if you have these partial product as multiples, as I've shown over here in this diagram, that you have these multiples already computed, so then you can use this full adder tree and then combine them together. And when you're going to combine them together, your multiplication is going to complete, right? So if you have these partial product, this Wallace tree is just showing how to reduce that to get a final answer. Okay, and it's going to take several steps to do that. Okay, so this is about Wallace tree. When you're going to come up to data tree, what you have to do is to maintain a level. So you have to maintain a particular step for that. For example, uh, if you have got seven inputs, so you go for a table like this where you it's shown how much steps is going to take to reduce it to two inputs. So seven lies here in between 9 and 6. So this means we are going to take 9. So this means it's going to take 4 steps. It's going to take 4 steps no matter what you do, right? So it took 4 steps also in Wallace tree. It's going to take 4 steps here as well, right? So let's see what's going to happen. So our first target is we have got 7 input, which is lying over here. So our first target is to reduce this 7 to 6. Okay. Then our next target would be to reduce this 6 to 4. Right. So first one, we have got 7 inputs. Looking at the table, we see that 7 inputs are going to take 4 steps, but they are going to they are going to take 4 steps if you reduce it from 7 to 6 in the next step. If you cannot reduce that, then they are going to take still more steps. So our first target is to reduce those 7 inputs to 6 inputs, and then from 6 inputs to 4 inputs, and from 4 to 3, and then 2. Right? So this is not the whole table. The whole table was shown earlier, but this is just showing you how many steps are going to be required over here. So let's see. Now our first target is to reduce it from 7 to 6. So it's not to aggressively use many full adders, but to use as many full adders as required to go to the next level. So if we have got 7 input, our next target 6 input, so we need just 6 full adders. And if you're going to use 6 full adders, you're going to see that each full adder is going to give 1 bit to that particular level and next bit to the next level. So you're going to see that 4 bits are already coming in as it is to the next level, and 1 bit is coming from this particular full adder, another from the previous one. So that makes 6. So you're going to see that 7 has been reduced to 6 by using 6 full adders. That's our first target. Once we reach 6, our next target is 4. So we are going to see how many full adders can be utilized over here. That is going to reduce from 6 to 4. So we have used 11 full adders in this second step, and then these full adders are going to reduce the number of operands from 6 operands to just 4 to be added together. Our next would be 4 to 3. It's not shown over here, but 4 is going to go for 3, and then 3 to 2. So we are going to use 7 full adders and at these places, and you have to just ensure that you don't miss any full adder. For example, if you're not going to use a full adder at this place, for example, it's 3 over here. You want that to remain 3. You could have skipped this full adder over here. In that case, what's going to happen is you might use a full adder at this point, right? But then this would mean that the next step is going to have again a 3 value over here. So this is not going to work. So that's why we have a full adder over here. Another thing that I can explain over here is this step over here. So if you don't use a full adder over here, assuming that it is 3 bit at this point, and we need 3 bit in the next step. But what's going to happen is in the next step you're going to get one input from this level over here. So if there are 3 bits and 1 bit coming from this, so in the next level you are going to still have 4 bits, right? So that's why we should use a full adder at this point, right? So in order to have just 2 bits at the next level, not 4 bits. Okay, so this is just showing you how to reduce it, and then we have used 6 adders, 11, 7, and finally 4 full adders and 1 half adder in the last step to give us finally 2 inputs to add. And then we can use a 7-bit adder, because we could have used a half adder at this point as well, right? But in a data tree, we're not concerned with reducing or combining the partial product as early as possible. If we have obtained 2 at a level like this, we are not going to disturb it. We are going to wait for the last adder to finally compute the result. So our target was to reach 2, and since if we have obtained 2, we are not going to use a half adder in this case in data tree. But in Wallace tree, we can use a half adder, right? So Wallace means that you are going to combine as early as possible. Data means that if you have attained that level, don't have to use any extra thing. So the resultant carry propagated at the adder at the last step in data trees are longer. You can see here there is a 7-bit adder. In the previous case, there was a 6-bit adder, right? The number of the total cost that was taken that was uh, that was used over here for this multiplication operation is 6-bit adder plus 28 full adders plus 2 half adders. So you can see you have got 6-bit adder, a smaller adder, 28 full adders, and 2 half adders. While in this design we have got 7-bit adder, which is a bigger adder, 28 full adder, and 1 half adder. So there were 28 full adders in this design as well, and 2 half adders in this design. But here we have just reduced just 1 half adder, but our 7-bit adder is quite big. It's the ripple carry adder is a little bigger adder. These are two options here that we can use for multiplication. Let me just go through a multiplier circuit, which is going to make this thing clear. But before that, let's take a small example. So let's say we need to multiply two 4-bit numbers. Okay, so a 4-bit number is going to produce a result like this. So we have each bit multiplied with these 4 bits. So they are going to be 4 partial products, right? So what I've done is inverted this, or you can say mirrored this, flipped this, and then it's going to come like this, right? This makes it easy for us to see how many bits have to be added. So this is actually the same thing here, but it's shown like this, right? So the maximum we have is 4 at any particular level, right? And now let's try to see how to reduce this. So we know we know that 4 will need 2 steps. So 4 is going to go to 3, and then 3 is going to go to 2. Okay, so let's see how Wallace is going to do that. So this is just one example. You can have your own example, which could be a little different than this. So what we did is we used 3 full adders and 1 half adder, which is going to convert that into so it's we could have used another full adder or a half adder over here, but it's not going to help us. So so that's why we have not used, but you can use it because in Wallace we can combine as early as possible. So by 3 full adders over here, we get 1 bit from this level, another bit from the previous level, and similar in the case is this. And so this 4 reduced to 3, and we can see here because we have not used a full adder, a half adder at this point, so we have obtained 3 over here, and that was our target. So we couldn't have 4 directly converted to 2, so 3 is okay. It shouldn't be 4. So if we hadn't used this half adder, that this full adder, this would have been a problem, because if there is a 3-bit and we are not using a full adder at this point, then 1 bit is going to come from this point over here. So 3 plus 1 would make it 4. So 4 remains 4. That's a problem. So we should use a full adder at this point over here, right? So from 4 it has reduced to 3, and then we have used 2 full adders and 2 half adders to obtain something like this, which is a 2-bit number, and three of these bits have been already finalized. So we just need a 4-bit CPA, carry propagate adder, right? So we or ripple carry adder. You can use any adder you want. So we need five full adders in total. So one, two, three, four, five. Three half adders, one, two, three, and a 4-bit ripple carry adder to complete this multiplication process, right? Now, if we go for a data example here, so in data we are basically concerned. So there are two examples shown over here for the same case. So if we go for two full adders, two half adders for the first case, so our initial target is to reduce from 4 to 3. So we are just concerned with reducing for 3. So we have not used any full adder in this case over here, or and a half adder in this case over here, like we did in the previous example. So we have used only which is most necessary. So we have used just two half adders, and these half adders are essential because if you are not going to use that this half adder in this case, the 4 remains 4, and if you are not going to use it in this case, then this means that 3 from this point are going to be combined with one more from this level, and then it's still going to be 4. So it's not going to be a reduction over here. So that's the least possible that you need two half adder. Here we have shown it with two full adders. Again, the same levels here that are essential. So this has reduced from 4 to 3. So you can see there are 3 levels over here. So now you need to go from 3 to 2. So for 3 to 2, you need all those where there are 3 to be reduced. And so that we have used a half adder over here and 3 full adders over here. In this case, we have used 2 half adders and 2 full adders. So our final design has a bigger ripple carry adder or carry propagate adder, and then the Wallace example. But if you can see here, you have using a less number of full adders and half adders. So here we have 3 full adders, 3 half adders. In the previous example, we have 5 full adders and 3 half adders. So you have 2 more full adders over here, but your CPA was a smaller one. Here we have two less full adders, but a CPA is a bigger one. So this is one example through which you can do it. This is another one through which you can do it. Again, you are not using 5 full adders. You are using just 4 full adders, and instead of 3 half adders, you are using just 2 half adders. But your CPA is a bigger one than the previous case. So these are two different designs that can be used to implement multiplier. So this is one example that we showed for multiplier. This is going to make it clear for you. So what you need is multiples. You need multiple shifted multiples. When you have just these shifted multiples, what you can do is combine them together in a haphazard way, because this is a haphazard way because we are using some full adders here. Some of the inputs are going to the next level, some of the next level, but finally it's going to give you the answer, right? So this design is a very fast design, but the connections are not very regular, right? But if you have these multiples, the other thing is you need to have all these multiples. For a binary case, the multiples are zeros and ones. For radix 4, you need 3a as well. So that multiple, if that's there, so you have all these operands with you, the shifted ones, shifted partial products with you. So you just have to add them together, which is shown over here. And this is a design showing you how to multiply to 7 by 7 numbers. So we have got 7 bits with one operand and 7 with another operand. And this is a multiplier. So you can see here this multiplier is quite complicated over here. So this is showing you a 7-bit CSA, which is a diagram shown like this. So it has got this 7-bit CSA is actually this circuit here, which is going to have 3 numbers of 7 bits, and it's going to reduce that into 2 numbers, right? So we have used that in a different way here, and so there are going to be 4 7-bit CSAs and one 10-bit CSA, and finally a 10-bit carry propagator, and this completes your multiplier. So you can see here that there are inputs going to other CSAs. So this CSA is basically 3 inputs combining together to form 2 bits, 2 outputs, 2 numbers finally. So you're providing them with these bits, and it's going to perform it in this way, right? So Again, this is a fast design, but it's a little complicated design to have, and you cannot expand it. If you want to increase it from 7 to 8, the expansion, you have to redesign everything with another number in mind. So if you are going to have a 7 to 7 and you want to convert into 8, that's not going to be possible easily. You have to you have to redesign everything. But this is a fast design because you have CSA tree combined in this way, which is going to give you finally your answer after a particular number of steps. Right, so this is the fastest one among the add multipliers, but it's not efficient in terms of VLSI realization. Okay, so then we come to array multipliers. So array multipliers have got a very basic CSA tree, a very one-sided CSA tree, right? And finally a ripple carry adder. So this is a design of an array multiplier. So you can see here that at each level, what you are doing is a multiplication operation, and the multiplication operation from one bit, because we are talking about binary numbers. So if a bit is going to multiply it with another one, so say for example, x naught multiplied by a, so x naught is going to multiply with a naught, x naught with a1, x naught with a2, x naught with a3, x naught with a4. So let's say if it's a 5-bit number, so you're going to multiply that bit with every other bit of the multiplicand, right? So it's an AND operation. So it's an AND operation. So what you can do is AND these and have these numbers with you. Then you can use these full adders. So these are the full adders shown as blocks. So a full adder has got 3 inputs. So you are going to giving them those inputs like this. So one of the input is 0 in the first level. The other input is x naught with a, the other input is x1 with a. So what you're doing on the top is actually x naught is multiplied with a. So you can see here a naught, a1, a2, a3, and a4. And on this side here, the third input that you're giving is x1 with a, which is x1 a3, x1 a2, x1 a1, x1 a naught. So x1 a4 is going to the next level, which is shown over here. So one of that bit is going over here. So this is going to compute. Um, so it's basically computing the same thing here, that you are providing it with one, but it's a very regular structure. So it's you are providing it with one bit to be multiplied with a4, and then another bit for multiplied by a4. So this is going to complete one level, and after that one bit would be finalized, which is p naught, right? In the second level, another bit is going to be finalized. Sorry, in the first level, this bit is actually already finalized. It's p naught, but this in the first level, after the first level, p1 is going to be finalized, and then you move on to the next level, right? Where you're going to have this inputs going at to the next level here, to next CSA tree. This CSA tree is combining 3 inputs and converting them to 2 inputs. So this is something similar to the one which we saw earlier. And then this is how computation is going to be performed in the next level. In the last level, you are having a ripple carry adder. So how many steps are we going to take? So we can do this in one step. Then the results are going to come over here, and we can do this in the second step, right? Then the results are going to come over here, and then we can do this in the third step. So all of these are already there. A naughts and x naughts are already there. The only thing is the inputs from the previous steps, right? So as soon as you are getting those, you can combine that and get it to the next level. So this is the same thing which was happening in ripple carry adder. So we were waiting for that results. So the same thing is happening over here, that the result is one of that result is going to the previous level, and another at the same level. So there are two results here, sum and carry. So sum goes over here, the carry goes over here, right? And then you are going to do 1, 2, 3, and 4. So fourth one is over here. And then finally we have a ripple carry adder, which means you can see over here, this design is a little different than the previous one. So you can see over here that the inputs are going to these full adders, but these full adders are connected in a different way. So 1, 2, 3, 4, and this would be the fifth one. This would be the sixth one, the seventh one, and eighth one. So after 8 steps, you are going to get your final results. So this is an array multiplier which is having a very one-sided CSA tree. So you can see that this is quite regular than than the CSA tree we saw over here. So this one is a irregular shaped CSA. It was combining 7 bits into two like this, and its connection were happening in a different way. But if you're talking about the array multiplier, these are very simple multipliers, and you can very easily see that what we are trying to do is we are performing an operation of 1 bit with the whole multiplicand and adding it with another one. So you're combining uh, two partial sorry two yeah two partial products together, and then you are going to the next step. So you're not talking about adding all of them together in one big step like we did in Wallace and data tree. So array multipliers are a little different. In array multiplier, we are not talking about Wallace or data tree. We are talking about doing it one at a time. So we are going to add one two inputs over here, two partial products over here, and then we go to the next step, and then we take that and add one more to that, and then we take that and add one more to that, and likewise we are going to do that, and finally we have a ripple carry adder. So this is not a very fast adder, right? Ripple carry adder, as it looks from the design, is going to take eight steps to complete it, which is not very good. If you compare it with the previous one, it was taking uh, say 1 2 3 4, and you got an answer for a 7 to 7 multiplier tree, right? So we have got 7 numbers. So of those 7 numbers, some of them goes to the here, some of them goes here, some of them goes here, and then the bit numbers are shown over here, which bits from which bits to which bits are going over here or here or here, and then finally we are going to get an answer. But as an array multiplier has a very one-sided CSA tree, so you are adding just 2 bits at a time. So if I just draw it over here, so what we are trying to do is we are going to go it slowly. So if I have to add multiply 45 with say 12, so or let me take a bigger number, 245 with 312. So what I'm trying to do is, first of all, 2 with 445. So 2 with 445 is going to give me something, and 1 with 245 is going to give me something, and I'm going to add these two together first, right? So whatever my answer comes, then I'm going to do 3 with 245, and then I'm going to add them together. So this is how it's happening over here. So this is not actually how we do it. So what we do is we get all these operands together and have a combined addition operation, right? But array is doing it 2 at a time. Okay, so array is doing it 2 at a time, and this is shown over here. So its advantage is not that it's fast adder. It's not a fast adder like this. Its advantage is something else. So it has got a slowest possible CSA tree, a slowest possible carry propagate adder at the end. So it's not obviously a fast adder, but it is very regular in structure, right? Which means that it uses very small or you can say determined interconnects from horizontally and diagonally, that you know that the delays are not going to change so much. So it has got an efficient VLSI layout, that's why it can be effectively pipelined. So this is the main point over here, that we can uh, pipeline this process. Okay, so pipelining this process is going to speed it up. Is going to increase its throughput. So that's the main advantage of array multipliers. Firstly, that you can, with their known wire sizes, you know that what their delays would be, so you can easily calculate their cycle times, and then you can pipeline them. And pipelining means that you are going to have it divided into different stages, and then some of the tasks for a particular multiplication would be done in one stage, and once that stage is complete, that multiplication is going to go to the next stage, and the first stage is empty, and so you can start on another multiplication operation. So adder multipliers are going to benefit you if you have got many multiplications to do in parallel. or coming one after another, not really in parallel. But if you have got many multiplication operations to perform, then array multipliers are going to benefit you because they can be easily pipelined. And we are going to show you how to pipeline an array multiplier. So this is a basic block here shown as consisting of an AND gate. So instead of writing that AND gate, we have included that AND gate inside that block. So the block here shown is consisting of these elements. So there is an internal full adder and an AND gate over here, and you can see here that the inputs here are four. So there are four inputs and two outputs. Okay, and actually full adder needs three inputs, so you have an AND gate which is ANDing the two bits together. So we have X naught and A naught together, ANDed together, X naught and A1 together. That's the same thing that was happening in the previous design, but in this initial level you have most of these bits as empty. So this first one is just going to compute X naught, A naught, X1, A1, X1, A2, because all the remaining ones are zeros. So full adder is just going to get one input. So this is going to be the sum input. So you're just going to get these sums. So you're not going to get any carries going to the next levels, right? Because the next level, what you're doing is A naught with X1. So that these two things were done in one step in the previous case shown. And why we've shown it like this, because we need to pipeline it, and so we have defined everything in a particular way that how it's going to happen in these stages. So if I go back to that slide, here you can see in the first operation we are doing two things together: x naught A naught with x1 A naught, right? So x1 and x naught, so both are happening in this first step, right? While in this newer design, what we are doing is we are first computing x naught with A naught, and then later on x1 with A naught, right? So that's the only change over here. And then the same thing over here till you reach the last step where there is a ripple ripple carry adder. So there is a ripple effect over here happening over here. So you're going to see that it's going to take 1, 2, 3, 4, 5, 6, 7, 8, 9 steps here, right? So now let's try to pipeline that. And when you're going to pipeline that, you need to figure out how many stages do you want to include. So let's pipeline that and include. Let's have 3 stages for this design because there are 9 steps here. So if we have 3 stages, then every stage is comprised of 3 steps. So we are going to divide 3 steps into one stage. So these 3 steps become one stage. The next 3 here become one stage. So if I draw that out, it would be something like that. That these 3 are going to be one stage, and these 3 are going to be the next stage, and these 3 are going to be the third stage, right? So this is going to take one cycle, one cycle, one cycle. So you are going to take 3 cycles. So for example, if you're doing it in a pipeline way, you need to have some kind of barriers in between stages. So those barriers are basically registers. So you need some registers in between, and these registers are controlled on some cycles. So you need 3 cycles, and then this computation is going to perform. So it's taking 9 steps, 3 cycles, whatever. But the advantage that you're getting is not because that you have reduced that you have not reduced the time, yet rather you want to increase the latency. You want to increase the throughput. So you can increase the throughput in this way that uh, if you have got many multiplications to perform. So for example, you have got to perform x1 with let me have a number like this. So for example, you want to have x1 with okay, x1 with x2, x3 with x4. So there are many numbers that needs to be multiplied together. So we have got x5 with x6. So they are, these axes are basically numbers coming one after another. So there are many multiplication operations to perform. So what will happen is, first you're going to start with x1 into x2. So x1 and x2. So assume that these, one of them is a, another one is x. So these both are going to be given to these are going to be applied over here, and then what's going to happen is, after one cycle, this x1 and x2 are going to perform three operations, right? And then they are going to move to the second stage, and there has to be some kind of a barrier which prevents a new inputs to go to the next stage, and that's controlled through a cycle, which is going to be controlled by a control unit here. So after the first cycle or three operations, x1 into x2 is going to go to its next three operations. But these units are now free because x1 and x2 have utilized them, and then you can use them for other purpose. So you're going to start x3 into x4 in this second in this particular stage, right? So x2 x1 and x2 goes over here, x3 and x4 starts over here. So after the next cycle you're going to see that x3 and x4 have done all these three, so they are going to go over here, and then you need some, again, a barrier over here like this that we had previous. So x1 and x2 goes to the last level, x3 to x4 goes over here, and then you can start a new one over here. So if you're divided into three stages, you're going to see that if you're divided into three stages, you're going to see that all these computations are going to happen in parallel. So they are going to overlap with each other. That's This is the pipeline diagram for that. So you can see here that we have provided x0, x1, x2, and we have used these registers as well. So these orange or yellow rectangles here are registers. Okay, so what's happening is you're going to give two numbers over here, and these numbers are going to be utilized at every step. So you can see here these bits are moving through the registers, and finally this red dotted line is the barrier over here. So after one cycle it's going to move over here. So all of that is now empty. So when it's empty you can start a new computation. So you're going to provide a new number over here, okay? And the previous number moves to the next stage. So when it completes these three, this one completes these three. So this means they have to be also completing at the right time at the same time, so that when the first number moves to the last stage, the second moves to the second stage, and you can start on with the new one, right? So this improves the throughput. So instead of having 9 steps to be taken, you can see that the effective latency would be just 3 stages. So you're going to see that every new multiplication is just taking 3 more full adder delay, and it's completing. So you're getting a result every cycle. But this is the only advantage is if you have a number of multiplication operations to do. So if you have just a single operation, obviously an array multiplier is not a good multiplier, because as we have seen here, it's a slow multiplier, has a very basic CSA tree, so it's not beneficial for a single multiplication. But if you have got many multiplications, then obviously you can use a pipeline array multiplier, and it's going to improve the throughput, right? Yeah, any questions till now? So we have seen the designs for multipliers. We have talked about the basic multipliers, boost multipliers. We have talked about how to improve the delays for the multiplier, how to improve that, means that how to make them faster. So we have talked about two different techniques for that. Use of uh, uh, less operands, less steps, means that you can increase the radiuses, or the second thing is to improve the addition process to go for full adder design, full CSA trees like Wallace and data trees. And then we also looked at array multipliers, which use very basic CSA tree, but the advantage is that if you have got many multiplication operations to perform, you can pipeline this into a pipeline multiplier and have many and have different multiplications happening at different stages, right? We could have divided it into say 9 stages as well. It all depends on how is your design. Obviously, three, if there are 9 steps over here, then 3 and 9 are the only stages that you can break that into. Otherwise, it would be of unequal duration, and to be of equal duration is better if you're talking about pipelines. Where we are going to come to the topic of pipeline when we are going to discuss instruction pipelining, but instruction pipelining is not the only pipelining. We can have pipelines in the functional units like shown over here. So this is an example of how to do pipelining in steps in multiplication. So we have divided the multiplication operation into different steps, and obviously you can see here that we have used a slow adder for this purpose, that we were intending to use it as a pipeline multiplier. So a normal multiplier is obviously array multiplier is a slow multiplier, but if you're talking about pipelining, that it's going to increase the throughput, and that's where you get the benefit. So let's this ends our multiplication topic. Our next topic is division. And hello.
सर एक क्वेश्चन था, जो हमारे पास प्रीवियस स्लाइड थी उसमें हमारे पास 8 स्टेप्स थे,
G.
तो ये 8 स्टेप्स थे, हमारे पास 9 स्टेप्स आ गए। सर सिर्फ इस पॉइंट को आप थोड़ा रिवाइज करेंगे?
Yeah, okay. So uh, what we did over here is we had this initial step just for parity, that this block is doing uh, an AND operation and getting inputs from two other places, right? Now, when you have a number, you can do just one AND operation over here because there are no two AND gates in this block, right? So what's happening over here in the first one is actually uh, x naught ANDed with a naught. So you are going to have an x naught coming over here, a naught coming over here, right? And nothing coming from these inputs. So what you're getting is x naught a naught. So this first level is actually doing this AND operation only. So you could have used an AND gate over here. You could have used, instead of these four uh, blocks, the whole circuit, because full adder is not utilized over here. You could have used just five AND gates. That's also possible, right? But the idea was to pipeline this, and when we are talking pipeline, we have stages taking equal duration. So we need to do the same task which is done in every stage. So which is going to take the same time. So if you're going to do something quicker, it won't benefit you. So the in this first level here, all these blocks are basically utilizing only their AND gates, not their full adders, right? Now what happens once you have this thing available to you, then you are doing another AND operation in this one, where you are talking about x1 with a naught. So here you have got x1 with a naught, right? And you are getting this input here, a naught x naught, from this level here, so which is part of their answer, but this level here is going to give you a1 x naught. So actually you are getting a1 x naught from this level, a 0 from this level, and internally you are getting uh, an a naught x1 over here, right? So if I draw this diagram, the full adder inside that block here, the full adder is getting a naught x1 over here at this point, right? And a1 x naught, sorry, a1 x naught from this point, and a 0 coming in from this point. So these are three inputs that it's getting, and then it's going to give a different output, right? For the second one, if I'm talking about this one, then it's going to be something like this. And you can see from the same thing here that this was done over here in one operation. So you can see here, okay, you can see here that this was done in one operation. So you're a1 x naught, a naught x1, sorry, a1, yeah, what is that? A1 x naught here, and where is that second one? We have a1 x naught and a naught x1. So a naught x1, yeah, a naught x1. So a1 x naught and a naught x1. So both are getting over here. Third input is 0, and this is computing your first full adder result. So this first step that is performed over here is shown here as two steps here because of regularity, because we need to use the same block at each place. So all of these are the same thing here. Okay, this is the only reason over here. That's why we have. Otherwise, you could have used AND gates at the first level, and you could have obtained, because in the first level you are getting all these inputs as 0, so you're just doing an AND operation over here. So it's only for the regularity. Okay. Okay, so now let's move on to our next topic, which is divider. So we have a few minutes. I haven't got much time to go on for the whole division, but we can just start this so that in next class we continue with bigger algorithms for that. So division operation is what is division operation? So when I ask you to divide a number with another number, what actually do I mean by division? So for example, if I ask you to divide, say, 74 by 6. Okay. Yes. Anyone? So how are you going to do that? Hmm? 74 by 6. Anyone? How do you start your division operations? So because we need to train the computer, not train the computer, we need to do that on computer. So we need to formulate ourselves how should our division algorithm work. Yes, what should be the first step of division? So what
So 6 12s are 72.
x 12, the 612. Okay, you came directly to that, but
So first we, I think, look at the MSB, and if it's greater than the divisor, or if it's less than the divisor or equal to the divisor, then we simply put it downwards and subtract it. And whatever the remainder is, then the next LSB or the lower LSB gets appended to that. Then we see if there are multiples other than 6, like 6 twos are 12, if it comes down like that.
okay, let's talk about this number now. 38 and 6. Hmm.
Now we'll look at both of the numbers together, because 3
Okay,
is less
okay.
than 6.
We are going to talk about both the numbers together. 38 now.
Yeah.
What to do now? Yes, what to do now? Come on, you know the answer. You know the answer. What to do now? How am I going to reach the answer in a systematic way? Okay, what's the answer? What's the answer?
6.3.
Okay, forget about the fractions. So the answer is 6 over here. So I need a 6 in my quotient part, and I need to have 36 over here, and 2 is my remainder over here.
Yes, sir.
Yeah. Okay. My question is, why 6? How did I reach 6? How did you reach 6? Come on.
So we started multiplying, and 6 was 36, 6 into 6, and that was
Okay,
less
okay,
than.
okay. So what you're implying here is You're using some kind of memory.
Yes, exactly.
Okay, so what you are using is a memory, but computer don't have any memory. Okay, so computer can have memory. You can store that tables, but they don't have a memory to search for if you have a different number over here. So for example, 6 and 7. So you need to store the tables for all of these numbers. So this can be any number over here. So storing a table for all of them is going to be quite complicated. So we need to do some computation. So what we are trying to do is what we are doing in our head is something different. So we are trained for that. We have learned those techniques over the years, and we know very easily how to do that, and so we reach directly to the answer because we know that 6, we need to find a multiple of 6 which is less than this number over here. So 6 into 6 is going to be give us 36 over here. So we are trying to do that. We shouldn't be bigger than 38. That's our first objective. So but if you don't know the table, what you're going to do is you're going to start doing it from 1, right? Because 0 is obviously 0. So you're going to start doing it from 1 and see whether that result is greater than 6 or not. So 38 minus 6, the result is quite greater than 6. So you increase that thing. So that would be now 12. So you do the same thing with 12. 38 minus 12, again a number bigger than 6. So you keep on doing that until you reach 6 into 6, which is going to give you 36 and a remainder which is less than 6. So you know now you have to stop. So this then becomes your answer over here. Okay. So this whole thing is made easy because you remember the table of 6. So you directly reach this point and you get your answer. But if you don't have this thing initially, then you have to do it like this. Okay, one thing more. If you don't know whether you can check this thing or not, so what is another thing is defined is that you go on with your next number, and that number is going to be bigger than 38. So you're going to get a negative answer over here. So if you're going to subtract 38 with 42, you're going to get a negative answer. So you stop whenever you get a negative answer. That can be another way. So you stop over here when you get a negative answer and go to the previous one. So that can be also another way of determining what should be our number, right? So when we come to multiplication, we have a dividend, we have a divisor. So we basically need to divide the dividend by the divisor. Okay. Now, because it's computer arithmetic and we have limited storage, so we need to define how many bits should be required for this process over here. So when you talk about multiplication, you multiply two numbers, 2k-bit numbers, and the answer is going to be, so if it's k-bit numbers, the answer is going to be in 2k bits, right? So if you go for a division process, it should be something related to multiplication. So if you have a dividend of 2k bits and a divisor of k bits, then you should get the answer in k bits. Okay. If you have a and b, and if you have one as k, another as 2k, then your answer is going to come in 3k. So if you have got 3k as dividend and 2k as divisor, then you are going to have quotient k. So things are going to get irregular. So to make them regular, we go with the same thing, k, k, and 2k, right? So if your dividend is 2k, your divisor is k bit, your quotient is going to come in k bit. So because divisor and quotient are going to complete the dividend, and you're going to get some remainder which is obviously going to be less than the divisor. So it's also, if this is k bit, this is also going to come in k bits. So in division, what you have to do is find a remainder s. We are going to call the remainder as s is equal to the dividend minus d into q. So our main operation is this. Or in other words, you can write the dividend is equal to d into q plus s, where d divisor multiplied by quotient plus remainder should equal your dividend, right? So this is a way to explain division, right? So when you're talking about division here, which is z divided by d, it's actually something like this. So we are trying to find out this number, which is d multiplied by q and s. So the problem with division is you have got two unknowns. So you have got two unknowns here and single equation. Okay, so you can have multiple answers. Right, I'm going to come to that. So there are different problems here. So this was just a bit form of how to do division. So when you're talking about division and the way we do it, we know how to do it. So it's a little different process than multiplication, because in multiplication we started with the left hand side, sorry, the right hand side, but in division we are always going to start from the most significant bit first, right? So we are going to start from the most significant bit first and not the least significant bit. So we are not going to start from this point, we are going to start from this point, right? So the same thing over here is shown in this diagram here, that if you have got a divisor here, you are going to go from the MSB, starting from the MSB onwards. Okay. Okay, formally I'm going to come to the algorithm later, but so division is complex because we have got two unknowns. So we have got two unknowns and we have got a single equation. That means that we can solve this equation in multiple ways. So z is equals to d into q plus s is, so we only know d and we only know z. So q and s. So if you fill this thing with different values, still you can solve for z. So how to resolve this? Anyone? Anyone? So if you have got 12 over here and I need to have a d of,
Remainder theorem.
what is that?
We used to do it in mathematics. We used to start putting values and whatever satisfies the equation, then that
Right,
would be.
okay, so my question is, I have this equation 24 over 2 into q plus s. So I can fill in q and s with any number and still I can get 24. So one possibility is 12 plus 0, but you can have any other possibility. For example, you can have 2 into 4 is 8 plus 4. That's going to be sorry, 2 into 10 is 20 plus 4. So q can be 10 and s can be 4. That's another answer. So but that's going to give me many answers. So can I restrict myself to one answer, and what that answer would be? So this is one problem over here. So we have got no one way of finding this. So, but we have one inequality over here, and that is that d should be greater than s, or in other words, s should be less than d, right? So d should be greater than s. That means that whatever remainder you have obtained is should be less than 2. Okay. But then there is a problem over here. If you talk about negative numbers, I'm going to come to that later. So that is going to give me just a single answer, because if I have this inequality over here, again I cannot get this answer simply by solving it, but I still have to do some kind of trial and errors. So I'm going to start with q of 1 or 2 and 3 and 4 until I reach 12. If I'm going to reach 11, so it would be 2 into 11 is going to be 22, and s would be 2. So 2 is still not greater than 2, so I need to increase the q and I go to 12. So 2 into 12 is now 24 and s is going to be 0, so 2 is now greater than 0. So this is where I'm going to stop, and I'm going to say the q is going to be 12 and s is going to be 0. So this is going to be my answer, and this is going to solve my equation. So this is how I do. But the problem is two unknowns, one equation, another inequality, It's not going to give me an answer easily. The other thing is that um the selection bit is not easy. Okay, so if we have binary number system, then it's okay. It's you have just a 0 and 1. But when you're talking about bigger radiuses, then there are many multiples, and uh, you need to subtract them with different values, and that gets a little difficult. The third problem here is that when you say that we have a dividend in 2k bits and divisor and quotient in k bits, then the problem is that quotient sometime is going to take more than k bits for the answer, right? So this is a case of overflow. So there is a possibility of overflow that your answer may not fit into the space that you have provided it with, right? So if you have got a number like so let's say we have got a 74 over here, and we need to divide it by 4. So if k is taken to be 1, because now we have got a 1 digit, so there is a 1 digit over here, 2 digits for dividend, so answer should come in 1 digit. This is what we expect, but this answer cannot come in 1 digit. Okay, so this answer cannot come in 1 digit, but you have just reserved 1 digit for it. So this is also one of the difficulties of multiplication, that the quotient could be greater than the k bits. So this can be checked by an inequality here, that since q is always less than 2k and s should always be less than d, then this means if you put the value of q in that equation, so this would mean that z should be always less than the shifted divisor. So this means if you are going to check the first few bits of the divisor and you see that this bit is less than that dividend, then obviously you can divide it without any problem. Otherwise you have to have you need more bits, and that's the case of overflow. So if I have the case over here, what I need to say is that we need to check, in other words, what is your divisor and the first digit here. So if your divisor is greater than the first digit, if the k is 1, if the k is 2, then you have to look for 2 bits, 2 digits, or 2 bits. So if 7 is less than 4, then there wouldn't be any overflow. But this is not the case. That's why the answer cannot come over here. So if I take the same example, instead of 74, let's have 34. Now your answer can come in a single digit, because here your first digit is less than your divisor. Okay, so depending on the k, you need to check those many bits or digits with this, and if it's less than that, then your answer can come over here. Okay, so I'm going to stop over here because the time is now 9 o'clock. So we are going to continue with division in our next topic, next class. I'm going to start from these are very simple concepts. I'm going to just go on with that. I'm going to start from restoring unsigned division algorithm in our next class, right? So we are going to start from that, and we are going to continue with our class at regular time next Thursday, because Eid is going to be on Saturday. So initially, I decided that because of Eid, we can have a class earlier on Wednesday, but now since Eid is on Saturday, so we are going to continue with our class next week, inshallah, on Thursday, right? Okay, so if there are any questions, you can ask. Otherwise, the class is ended. So I'm going to upload the slides as well as the video links by tomorrow or maybe today, if it's ready. And yeah, I'm going to also give you the book chapter for multiplication and division, so you can read it yourself as well. Okay, are there any questions here?
No, sir.
Okay, thank you then. Allah Hafiz.
अल्लाह हाफिज़।
अल्लाह हाफ़िज़। इकबाल अजीज याजी दिया।
अस्सलाम वालेकुम सर।
जी वालेकुम सलाम।
सर वो प्रीवियस वीडियोस आपने अपलोड अपलोड किए हैं या?
आप नहीं नहीं अपलोडेड हैं वो, आप अगर क्लासरूम पे जाएंगे तो आपको सब मिल जाएंगी।
अच्छा
वो सारी वीडियोस जो हैं वो अपलोडेड हैं। और दूसरा ये कि हाँ, लास्ट टाइम बल्कि आप कौन सी दफ़ा कर रहे हैं ये बताएं, मैं तो भूल ही भी गया। इतनी दफ़ा
सर।
आपने किया है ना, वो तो ये भी याद नहीं रहता कौन से टाइम, और हर दफ़ा जो है ना या तो मिड टर्म से पहले ख़त्म हो जाता है या फिर उसके बाद जाके फाइनल में तो आता ही नहीं है।
सर अच्छा है आप भूल गए। अच्छा है सर, नए से शुरू करते हैं।
हाँ, नए शुरू करें, थोड़ी मेहनत करें इस दफ़ा और इंशाल्लाह फिर हो जाएगा। इसमें थोड़ा सा वो है कि लास्ट टाइम क्या था, लास्ट टाइम क्यों नहीं किया था आपने? क्योंकि लास्ट
सर
वालों में तो काफ़ी आसानी हो गई, क्योंकि वो जो सेटिस्फैक्ट्री ग्रेड आया ना तो उसमें सब निकल गए।
नहीं सर, असल में तब मैंने नहीं लिया था ये कोर्स।
सही है।
हाँ
चलें
सेटिस्फेक्ट्री।
इस दफ़ा मेहनत करें, इस दफ़ा मेहनत करें, इस दफ़ा इंशाल्लाह निकल जाएगा ये।
इंशाल्लाह सर, मसला यही है कि मेहनत ही नहीं कर पाते, टाइम नहीं निकल पाता, अदरवाइज इंशाल्लाह लाजमी निकालना है इसमें।
हाँ, इसको निकालना है आपको फिर।
जी
ठीक है।
जी। ठीक
चलो,
है सर, थैंक यू सो मच,
थैंक
अल्लाह
थैंक
हाफिज़।
थैंक अल्लाह हाफ़िज़।